Hi kidlets, this is your second notes video for light and telescopes. This one is just going to go through spectroscopy. The next one will be beginning with optical telescopes. So just as you guys have already done in your lab, we can tell just by looking at the starlight, the incoming starlight that we can analyze, we can talk about and learn about the total energy output of the star, the temperature, the size, the chemical composition, how close in proximity it is to Earth, and its rotation. From all of those different things, we can determine the life cycle of the star. We can determine what its fate is going to be. Is it going to be a supernova that is going to eventually possibly be a black hole? Things that could affect us. Is it going to send interstellar material out through the vacuum of space? Those are all things we would want to know. And we can know all of that by looking at spectra. So spectra is like the fingerprint of a star. It is specific to every element, and no element, just like none of you have the same fingerprint, no element has the same spectra. So by just looking at a star's color, we can determine what temperature that star is. So they appear in different colors because each color has its own specific wavelength. So we can see just by looking at the constellation Orion, which is of course my favorite constellation, that the star Betelgeuse, which makes up the shoulder, here you can see the belt stars, there's the sword, there is one foot, there's the other foot, there's shoulders, he's kind of standing sideways, up here is his head. We can see just by looking at his shoulder that Betelgeuse is red and Rigel down here is blue. Those indicate different temperatures, different phases in their life, and also different fates. Rigel is way hotter than Betelgeuse. So these tell us about the star's temperature. So whereas the spectra can tell us a little more about the composition. So stars are black bodies, which means they are both perfect emitters and perfect absorbers. And a perfect black body would, at room temperature, which stars obviously are not, would appear black, hence the term black body. So each stellar spectra has an approximate thermal spectra as well, and the maximum black body is the temperature at which the wavelengths are at their highest. So we can see, just looking right here, that the highest wavelength peaks in the blue portion of the spectra, which would mean that the object is about 7,000 degrees. Here we can see the peak is about in the green, which means it's 6,000. So we can tell just by looking at the black body spectra, the peak of the highest wavelength, we can determine what the temperature of that object is. So the temperature would be concentrated in this narrow band of wavelength, and the peak is where that black body radiation is, the highest wavelength. So there are two different laws of black body radiation. Essentially, the hotter an object is, the more energy it's going to emit, not just absorb, but emit. So the bigger the surface, the higher the energy flux. You don't need to know your equations. Notice they have the stars, so those of you that are interested in further study, you could take a look at that, but you don't need to know that. Those might be things that I would give you an option on a test of either writing an essay or maybe solving something, but I probably wouldn't give you this one. But you would just need to know that essentially the hotter an object is, more energy it's emitting, and that's called the energy flux, which kind of makes sense. The second, which should actually be relatively intuitive at this point, since you know the relationship between energy and wavelength, and thus frequency and wavelength, because they're inverse. So as the temperature increases, that means the black body spectrum, remember the peak of the highest wave is going to shift towards shorter wavelengths. So if you understand that wavelength, remember the length of the wave, and frequency, the number of times the wave occurs, are inverses, they're opposites. One gets longer, the other gets shorter. Just know that temperature can be associated with your frequency, with your energy. They're inversely proportional. So as you have an object that's getting hotter, it's going to be shorter wavelengths. Thus, that explains why blue is hotter than red. And we can express that with this equation, which of course got super functified when I uploaded to this app. This box should actually be over this. If you just take 3 million, the length of your wavelength, and divide it by your temperature, you get approximately what the maximum wavelength is. So that should be lambda, not L, but my app doesn't like that Greek symbol. So we can determine what the wavelength is if we just know what our observed black body is. We can determine what that max wavelength is. So an example of this would be, looking at, say, a fire. So we know that before you can even see the colors of a fire, before you can see sparks, you can start to feel the heat. So that would be your infrared. And as it begins to glow, it goes first from your red to your oranges, then eventually to blue and white. So it's going to be shifting to shorter and shorter wavelengths. So this direction, as it gets hotter. So then using Wien's law, so if we know approximately the nanometers of that portion of spectra, we can just use that simple formula to determine what wavelength it is and which color. So an example of this would be, say mammals that have a temperature of 300 degrees Kelvin. So then we know if we just take 3 million divided by 300, we get a spectrum that is in the infrared. So if you think about mammals that see in infrared, they're nocturnal. So all mammals that are nocturnal have to have this sort of body temperature so that they can see in the infrared wavelength. Another example would be a fire that burns at 1500 Kelvin. You take 3 million, divide by 1500, and you get a portion of the spectra which could tell you, is it a really, really hot fire, is it raging in the blue, or is it raging in the red? So the Doppler shift is another way of expressing our wavelengths. So remember that Doppler shift has to do with sound, whereas visible wavelengths we could see in redshift, which is what you guys did in the lab. So the Doppler shift is the change of wavelength due to the apparent motion of an object. So examples would be fire engines, and we can apply that to astronomical objects such as rotating things such as planets, stars. We can use it to determine distance. This is also used to determine if a star has an extrasolar planet orbiting around it. So if you think about a police car as it's moving towards you, you can see that it's compressing all of the sound waves in front of it. So the pitch is going to go up as it approaches, and as you're standing back here seeing it move away, it is elongating all of the waves as it moves away, so you would hear the pitch decrease. So that's for your sound. If we were to apply the same concept to a rotating object of light, so photons, we would call that the red shift and the blue shift. So we know longer wavelengths are associated with red. So as a surface is rotating away from us, just like the police car is moving away, it would be shifted red, and as it's moving towards us, it would be blue. So comparing those two different things and the ratio between the red and the blue, we can determine a rotation period. This can also be applied to galaxies to prove that galaxies are all moving away from us. And this is what Hubble, on top of Mount Wilson in Pasadena, did in the 1920s. He noticed that all galaxies are red-shifted, so meaning that they're not expanding themselves, that the space between them is expanding. The universe is expanding. So the way we can determine what sort of wavelengths each portion of light falls in is by using a spectrograph, which is essentially acting as a prism, which is slowing down the wavelengths of light into each of their individual wavelengths so that we can see the full spectra, the full rainbow. Then when we add in a grating, a diffraction grating, we can physically measure what each of those wavelengths are. It gives us an actual value. So the spectroscope is going to split light into each of the component colors. So you guys were able to look through this and able to see that. So if we look at, say, a light source here passing through a diffraction grating or a prism, we can then see all of the color here. We could see the red light focused on one side, the blue on the other. So long and short wavelengths would be separated. So an astronomer in the 1800s named Kirchhoff was able to formulate these 3 different laws of spectroscopy. So he formulated that there were 3 different types of spectra. We had continuous spectra, emission spectra, and absorption spectra. So, and each of these you were able to see in the lab, and we'll take a look at each of those. So if we were to look just at a full rainbow, so just the source of illumination, so say just the sun, something that was not being absorbed by anything else or didn't have any filaments that were emitting additional light, we would see just a continuous spectra. Whereas we would see an emission spectra, which remember is the one with the black background and the colored lines. So that would be if there is something that is a low density hot gas. So that hot gas would be what would be emitting your emission spectra. And you guys were able to see that with all of those gas tubes. Those should have all been emission spectra. So those would be something that is very hot that is emitting each of those spectral lines. So each element you would be able to see an emission spectra. Then our absorption spectra would be as that light is passed through a cool, thin gas. That gas would be absorbing different wavelengths of light. So absorption and emission spectra are actually opposites. If you line them up, each of the lines would be in exactly the same spot. So here we can see emission lines. So as this hot heated gas, or like each of your different gas tubes passes through, they would give us these lines at specific wavelengths that would be specific to that element. So here are some emission spectra for hydrogen, sodium, helium, neon, mercury. I believe we had all of these in our lab. We can see neon concentrated much more towards the red and the yellow, hence neon lights. We can see hydrogen concentrated much more towards the blue. So our absorption spectra would be if that light was passed through, so here's our light passing first through a cool gas. So then we would see these absorption lines as that gas is absorbing specific wavelengths. So this would be what our sun would be producing because the outer layer of the sun is cooler than the inner layer. And here is the absorption spectra of the sun. You can see there's a lot of different elements in here. So this is created when you have atoms that are excited beyond the ground state. So when you have atoms that absorb specific wavelengths of light, and it has to be the same wavelength or the exact same energy as that electron. It's not like it can just absorb anything. So absorption is when it moves up to a higher energy level. So it would be moving up, which is the non-natural state. The ground state is the natural state. And emission is when it falls back down. So again, absorption goes from ground to excited, and that is a temporary state. And it emits when it falls to a lower energy level, the ground state, which is the. So here is a little description of the ground versus the excited state. So here's your incoming photon. It has to be a photon at a specific wavelength for that atom. Not any one will work. We'll excite it up to the excited state, and here again is the inner ground or natural state. So here is each of those different laws illustrated. Here we can see just the heat source would produce your continuous spectrum. Your heat source going through a cool gas would be your emission spectrum, and the spectrum of just the cool gas would be your absorption. And here is that broken down again, showing just what you would see. Your continuous, your absorption as it passes through the cool gas, and just the gas would be your emission. So stars of similar temp would have similar spectra. So instead of looking at every individual star, we can look at different types of stars and classify them. So this is the letter designation that Annie Jump Cannon and the other computers at Harvard University gave each of the different class of star. You can remember this from the ridiculous acronym of O, be a fine girl, kiss me. So O being our hottest star and M being our coolest star. We are around a class G star. This is like our sun. So you can see we are very mediocre in terms of temperature. And here is that again. So here's spectral class. Here showing the color. Here the general temperature, and here where your prominent absorption lines would be. So for our sun, we're a class G star. So we've got some weaker hydrogen lines, we've got some calcium lines, but you can see up here you have some heavier elements. So elements heavier than your oxygen and carbon can be fused in these stars. So here is where we are going to stop. So G, yes, we have a yellow star, and yes, there are blue and white stars.